So who here has a background in robotics? Just show of hands. Okay, like three people. All right. Okay, so we are Twan, Koolen and Robin Deits, and we are PhD students at MIT at the Robot Locomotion Group. So we focus on legged locomotion, so bipeds and quadrupeds, and most recently we worked on this big project called the DARPA Robotics Challenge. So the challenge was to complete a number of tasks, such as climbing stairs, traversing rough terrain, opening a valve with a humanoid robot or with a robot platform. Here are some other videos showing our work. So Robin has worked on some trajectory optimization stuff involving quad rotors with mixed integer, or with convex mixed integer optimization. In a previous life, I worked at a research institute called IHMC, where I did push recovery for humanoid robots. And these bottom two videos show more of our work related to the DARPA Robotics Challenge. So footstep planning and autonomous locomotion. All right, so what kinds of computations do roboticists do? Well, at the lowest level, you need to somehow provide pretty low-level commands to your robot, right? So torques, for example. And that needs to happen at maybe 100 to even 5,000 hertz. And so the input for that is typically some kind of joint trajectory in terms of desired positions, velocities maybe. And the method you would use for that is a linear solve or maybe a QP. And this would happen at a really high rate online, and it needs to be very reliable. Then at a slightly higher level, you need to do some kind of trajectory optimization to come up with a trajectory that brings, for example, the hand of the robot from its initial position to some goal position while avoiding collisions with obstacles. And then at an even higher level, you need to do this POMDP type stuff that was talked about earlier in the conference. So these are sort of our biases. Oh, wait. Well, let me first do our biases. We are kind of low-level people, so we don't really think about these high-level decision problems. We're closer to the hardware, let's say. We have been very blessed with super high-performance hardware. So the robot we showed in these videos, the Atlas, has 3 i7s on board, for example. We very much prefer open source solutions, like a lot of people here, I think. And sort of a specific thing about us is that we don't use ROS much. So ROS is very popular, but we don't actually use it that much right now. ROS is, it's a robot operating system, but it's not quite that. It's not an operating system. It's a middleware. So it passes messages between processes, for example, provides all kinds of other tools as well. All right, so apart from these sort of control-related tasks, there are other tasks. You need to do some kind of dynamic simulation to make sure that your software works before you break the robot with it. Parameter optimization for design or for system identification so that you can have a good model for your controller. Finding control laws, so synthesis, or finding out when they work, analysis. And so these are pretty different requirements, varied requirements. All right, so what do roboticists want from software that performs these tasks? Well, first off, there are like 2 groups that you have to cover. The casual users or just students who just start to learn robotics. And for those people, ease of installation is important, great plotting and visualization. Honestly, MATLAB or Python like syntax, a lot of casual users don't know C++ coming in, and then if you have to teach a class where you both teach C++ and teach them robotics, that's really tough. Multi-platform, not a lot of people come in with Ubuntu, for example. There are a lot of Windows users, and you want to have a pretty gentle learning curve, obviously. All right, so then the other group is power users. So what do they want? Well, maybe those last 3 bullet points go away, but you still want those first 2 definitely, and then a whole lot more. So you need performance. People care a lot about performance, and there's this sort of specific requirement that's specific to robotics, which is this real-time guarantee, right? You want to be able to guarantee that that the control algorithm delivers new desired motor commands at a high enough rate. And then there's this whole list of other things that you need to cover. So currently, people use some combination of MATLAB or Python and C++ and maybe Java, although that's not very common. And then there's Lisp, which some Japanese groups use still. And I put it in parentheses originally because it's not used that often, but it's also kind of a pun, I suppose, in the end. All right, so there's a definite 2 or more language problem in robotics. And so maybe Julia can actually solve that kind of thing. So I'll give it over to Robin now.
Hi, everybody. Yeah, so I'm going to talk a little bit about what tools currently exist, and then we're going to show some of the things that we've built, and then talk a little bit more about what's the future of robotics in Julia. So this is a somewhat biased selection of Julia robotics tools. Most of them we had nothing to do with whatsoever, but we think they're cool. So there's Caesar, which is an estimation framework. There's the Julia MPC group, which is Huck Febo, who presented earlier. Julia Control, Julia PalmDP. There's RobotLib, which interfaces to kinematics. And there's Robot OS, which interfaces to ROS. And I even have some Lego Mindstorms bindings in Julia. So that's in the bottom right there. So the first thing I want to show that we built is called DrakeVisualizer.jl. And this is a visualization tool that we're going to use to show 3D geometries and move them around. So it's built on top of a C++ and VTK app that was developed by Pat Marion, who's a student in our lab. But it has nice Julia bindings that hopefully make it easy to create and transform 3D geometries. And we're going to do this by having Julia talk to the visualizer using LCM, which is a message passing protocol. So it's a little bit similar to 0MQ. And as a result of this project, this sort of spun out a couple of Julia packages that you can use. So LCM Core is a very low-level binding to this messaging library, and PyLCM gives you nice high-level syntax by leaning on Python. But you're here for the demos. So let's do that. So I just want to show easy visualizations in Julia. Cool, it's all good. All right, so all we have to do is import our package with using Drake Visualizer. We're going to make a handle to the visualizer itself. And if we want to add some geometry to that world, all we have to do is set geometry. And so this hypersphere you might recognize from geometry types. So I'm leaning on Simon's work for all of the representations of geometry because I don't like doing work. I'm leaning on coordinate transforms for all the representations of homogeneous transforms because I don't like doing work. And I'm leaning on Tim Holly's code for all the color stuff because I don't want to write that either. Okay, so if we're going to make a robot, we could make it a sphere, but spheres are pretty boring. So let's make our robot a cat. So we support meshes because, again, I'm leaning on the mesh.io package, which I didn't write, but everything just works. We can add an arm to our robot. So I'm gonna make it a child of this base, make it a rectangle. So now our cat has an arm. Okay, so now it's a robot. And now because the arm is a child of the base, I can move the base, and the arm moves too. That's cool. But we can just move the arm, and that moves. So now we've made a fully functional robot. And we can lean on more code that I didn't write using interact, and now we can use this and actually manipulate our robot. So now we have a fully functional 3D robot model in very little code. So that's pretty easy. Cool. So that was nice. Let's maybe actually solve some robot problems using this. So I want to solve a very, very simple toy problem, but that's actually representative of the kind of work we might actually do. So this is called model predictive control. The idea of model predictive control is that we're going to run a fast optimization online on a robot to choose the robot's next actions based on predicting its future state. So we're going to predict maybe a 1-second time interval and choose some actions that will optimize a cost. So get the robot to a goal, keep it upright, do something sensible. And the nice thing is that, again, Julia gives us all kinds of great tools that we don't have to write that we can use to make this really easy. So I'm going to lean heavily on Jump for this and Gurobi to actually solve the problems. and that's in this tab. So I'm not going to go through this optimization entirely in detail, because the details aren't super important. But I just want to show you that jump makes it pretty easy to write down something that kind of looks like what you would actually read in the paper about this. So I'm going to create variables for my position and velocity of my robot. I'm going to create variables for my acceleration. That'll be the input that we're going to pick. And I'm going to constrain that, sensible things like acceleration is the derivative of velocity, and velocity is the derivative of position. And we're going to have some cost function like, let's try to minimize the position of the robot at the end of the trajectory and the velocity at the end. OK, cool. So that all works. What does that look like? So I'm going to draw a robot as a box. Sorry, not a cat this time. And I'm going to draw a circle at the origin where I want the robot to end up. And so I can run one round its optimization, and so I can show you where the robot is now and where its planned motion is over time. So it's going to go to the origin. So that's cool. But that's not really how we do MPC. We run MPC, we're running this optimization brand new from scratch every time. So every time step, we're going to run this optimization, make a plan for the robot, and then execute the first part of that. So that's this whole thing. This is an entire MPC controller in Julia. It doesn't take much code. So at every step, we're going to run the MPC optimization, draw the result, apply the plan, and integrate with, Chris, don't look, the world's worst forward Euler integration. I promise to use differential-equations.jl tomorrow. And so what that looks like is this. I've bounded the acceleration to the box, so it's not allowed to go straight to the goal, but it's going to do something sensible. And so I can start it from a random place, and it will do something pretty reasonable. Yeah, so that was super easy. And this is the actual kinds of model predictive control problems that we would solve in a robotics lab.
All right, so that was a kind of a very simple example, but if we want to control these more complicated humanoid-type robots, then one of the base building blocks that we need is a rigid body dynamics library. So I wrote rigidbodydynamics.jl with a little bit of help from Robin as well. And so I had three main goals in mind. One was fast kinematics and dynamics algorithms for use in simulation and online control at that high rate of 100 to 1,000 hertz. Then gradients with respect to both the state and the parameters, so masses and stuff, to enable trajectory optimization using gradient-based methods and system identification. And then also symbolic dynamics, so that you can do synthesis and analysis. And then fourth, and which I think is very important, good user experience, because a lot of existing fast libraries out there just don't provide that. All right, so here's a quick demo. All right, so we're going to simulate a double pendulum, which is still a very simple robot, but it's a little bit more complicated than what you've seen so far. So there's this URDF file format that's used in ROS as well. It's basically an XML file format, and I can just load that directly into using my package. Then let's visualize this double pendulum. So here it is. Just like before, we can use manipulate to change the angles. And then let's simulate starting from this initial state and animate the results. So I can also animate while you're simulating. I'm not showing that here. All right, so then some other stuff. Here's doing kinematics. So first I'm just going to unpack the joints of the robot. So there are 3 joints in this robot. The first one is just a fixed joint that has no degrees of freedom. Then I'm going to pick one of the frames that are attached to the links of the robot. And here that's going to be the frame directly after this elbow joint. So I can visualize that here. So this is the frame that I mean. Then in that frame, I'm going to define a point, namely the tip of the last link. And that's over here. So note that the point 3D type here actually has the frame information in it, which is a pretty nice feature. It allows pretty cool things that I'll show in a second. All right, so let's take this point and transform it to the world frame. So world frame has axes over here, basically. I should have visualized that, sorry. So you can just transform it using this state object that we've defined earlier. And then one of the sort of common mistakes that people make when writing control algorithms is adding things together that are expressed in different frames. So I've tried to make that impossible by checking just before performing the action whether the frames actually match. So here's some other points expressed in the frame after the elbow. And then we can, of course, do tip minus other points. That's fine. But if you do the tip expressed in world frame minus other point, you're going to get an error message explaining exactly what's wrong. And now, so this has some overhead associated with it, of course. But if you run Julia with bounce checks turned off, then all of that code will just be elided. All right. Then, just as a simple example of some dynamical quantities that you can compute, here's the mass matrix. So here, this version allocates, but there's also a version that doesn't allocate at all. So mass matrix bang, basically. All right. So that's sort of the simulation and fast control part. Then this is the symbolic part. So using this SymPy package, so SymPy is a Python library, obviously, that has pretty good Julia bindings. We can just run SymPy types through our dynamics and kinematics algorithms and just get the symbolic answers out. So here, let's define a bunch of parameters. So these are just the masses, inertias, link lengths, centers of mass, and gravity. So here is sort of a different way of defining mechanisms. So instead of using this URDF parsing thing, this is more a programmatic interface. I'm not going to show you exactly how it works, but it's not too bad to define a robot in this interface either. So now I'm going to make a symbolic mechanism state object, set the configuration to just some symbolic variables, and then here's the mass matrix in symbolic form, and kinetic energy, gravitational potential energy, and so on. All right. So there's some basic support for closed-loop mechanisms as well. There are still a couple of to-dos, but the basics are there. And here's a video of Valkyrie, another robot we have in our lab, waving. So this is a simulation with a controller in the loop. So we created a controller that's solving a QP online that basically resolves the available contacts with the desired motions we want to execute and comes up with torques that then go into the simulation. In terms of performance, I'm not super happy with the performance yet. It's pretty decent, but it needs some improvement still. What I am happy with is this column allocation. So we're already at 0 allocation for most of the main algorithms, or all of the main algorithms. All right. Oh, wait, sorry. So additional features. I really wanted to make this really easy to distribute. So I agree with some of the other speakers at this conference that it should be very easy to distribute code with your paper and have other people run your code to make sure that it works and to see how it works exactly. So minimal dependencies was a pretty big constraint for me. Singularity-free dynamics. So I use over-parameterizations of rotations everywhere. Caching intermediate results. So if you compute the mass matrix and then you do inverse dynamics, then some intermediate results stored in this mechanism state object will get reused. So you get a little bit of a speed up that way. There are various ways of modifying your mechanisms. So if you have a model of this Valkyrie robot, this whole humanoid robot, but you want to simulate just its arm, you can do that. You can attach one mechanism to another. So if you want to attach a third arm to Valkyrie, you can do that in a programmatic way. Maximal coordinates, I'm not going to explain. And I wrote a specialized ODE integrator. Hopefully, at some point, I can use some ODE stuff from the Julia ecosystem. All right, so future work for the rigid body dynamics.jl package. So these performance improvements that I talked about, finishing support for closed loop mechanisms, and specifically what I need to do still is make sure that the constraints don't get violated after some time. So currently the constraints are enforced at the acceleration level, but I need to do some constraint projection or stabilization in order to make sure that they are enforced over a long duration simulation. And initial constraint resolution using a nonlinear program. Then contact, so I showed you Valkyrie balancing on ground. Currently the only primitives, like contact primitives supported are half planes, so the simplest possible thing. And it's a penalty-based contact model. I want to try this other approach to solving contact problems using a linear complementarity problem formulation. All right.
Hello again. So beyond just improvements to rigid body dynamics, there's a lot of cool things that we're hoping to do in the future with Julia for robotics. So I'm personally working a little bit on combining learning and optimization. So specifically, I spent some time a couple weeks ago hacking together a very, very poor neural network library just based on reverse diff, which worked way better than it had any right to. So kudos to Jared for that. And I'm interested in making that better. We're also looking at new ways of solving robotic optimizations. So we've both done a lot of work in these convex optimizations, mixed integer convex optimizations. Maybe we should not be doing that. We started, as of yesterday, exploring using David Saunders' package, interval optimization, to just globally optimize the functions we actually care about. That turns out to maybe actually work, which is going to be cool. We're also interested in geometric representations, so I'm hacking on some tools for polyhedral representations, and another student in our lab is thinking about more ways of decomposing polyhedra. But the real big one is controlling real robots in Julia, because simulation is great, but it really doesn't count until you have it on an actual robot in the world. So, questions for the future to make all of that happen. Julia is great for performance, but as Twan mentioned earlier, for robotics we need reliable performance. So that means low jitter, for example. That means that probably if the garbage collector pauses for 10 milliseconds, the robot's going to die. If the JIT compiler comes in and hangs the thread for a minute, the robot's definitely going to die. So we have to avoid all of that. We can get away pretty well by just avoiding memory allocation and making sure that we have type-stable code so that we're not invoking the compiler at runtime. But it's something that's always in the back of our mind, is that like work will be needed to make sure that the controllers are not just fast on average, but fast every time. We're also interested in how can we make jump or convex.jl even faster. So jump is amazing, and it's much faster than any of the other similar modeling languages, but it's still not fast enough to be running inside the innermost loop. So if you're constructing a jump model at every iteration, you're not going to hit the kilohertz performance that you actually need. But there's got to be a better way. I don't know, maybe cassette or something? The other question is, how can we run this on less fancy robots? So it's nice if you have 3 i7 desktop machines running Ubuntu on board your robot, but like realistically, future robots might not have that. Julia is a pretty big dependency. So I actually tried getting Julia to run on the LEGO Mindstorms EV3 brick, which has a whopping 64 megabytes of RAM. That did not work, despite some very helpful advice from some of the devs. It also doesn't have floating point numbers. So, but maybe in the future, when we take LePac out of base, we'll have a non-floating point Julia. And the other questions are, how can we get even more speed? So Julia is super fast, but there's still a few tricks that we can play in C++ that we can't yet do in Julia. One of them is fixed maximum size arrays. So if you're not exactly sure how big something is, but you know how to within what range it will be, you can make nice stack allocated things in C++. That's harder in Julia, but I have hope. So we have showed you a whole bunch of things. So we showed rigidbodydynamics.jl, which is a pure Julia dynamics library for simulation, modeling, kinematics. We showed rigidbody tree inspector, which was how Twan made the little arm thing move around with interact. We showed Drake visualizer, which interfaces with a bunch of other code outside of the Julia ecosystem to draw stuff. We showed LCM Core in the background doing all of the message passing work. There's a whole bunch of other things that we didn't show. So nnls.jl is a non-negatively squares solver in pure Julia, which we're just as of this week trying to turn into an available solver for QPs in Jump, because it seems to be super fast for small sort of robot-sized problems. So if you would like your Gurobi models to be solved faster, we might be able to help. We also have flexible nonlinear program.jl, which Twan wrote, which is another mathprog-based extension for general purpose nonlinear programming. There's enhanced gjk.jl, which builds on Simon's geometry types to do collision detection between meshes faster, and that's also pure Julia. There's a bunch more. There's some adaptive distance stuff, pictures I didn't put in here. Yeah, so if you have more interested in Julia robot tools, there's a good chance we've at least thought about it. That's all the stuff we've done, but none of this would have been possible without the stuff that you all have done. So in particular, we're very grateful to Jump and the whole Julia Opt organization for providing us with all the solver interfaces, because holy crap, we've actually written solver interfaces in other languages and no one should ever have to do that again. Thanks to the Julia Geometry and Simon for all of the primitives and meshes and mesh loading and all of that great stuff. Static arrays, so Andy and Chris, and rotations for all of our ridiculously fast arrays, without which none of the zero allocation stuff would be possible. Thanks to Jarrett for forward and reverse diff and all the other collaborators at Julia Diff, because that's how all of our Jacobians and things work. SymPy, JL, and of course the Julia core devs, because, I mean, otherwise we wouldn't be here. If you want to see all of the demos that we showed and a link to the slides, it's on GitHub right here. So t:/robotics.juliacon2017.jl. That's all, and thank you, and please let us know if you have any questions.